Hello everybody, and welcome back to another CIV 398 assignment tutorial. So in this tutorial, we're going to be covering question 5 of assignment 3, and I got good news and I got bad news. The good news is question 5 is the last marked answer, and I used marked in air quotations because of course we have the bonus question. But the good news is we're almost done assignment 3, and hopefully it hasn't been too bad so far. Now, the bad news is if it hasn't been too bad so far, this is the reason why. And please don't hate me for this. Question number 5 kind of sucks. It's a bit more intuitive, and you're going to have to do a little bit of thinking. And you're thinking, oh, thinking? I don't want to think. Well, this is why this question probably won't sit well with a couple students, is because you have to really think. But this is a really good question in order to figure out what exactly is going on with position functions. So question 5 states, the reference and deformed configurations of an object experiencing two-dimensional motion, so u3 is equal to 0, is shown in the figure below. And I don't have the figure, but you guys have the figure. You guys can see what's going on. And the coordinates of the deformed shape are a prime, b prime, c prime, and d prime. So what you guys will get is you guys will get random coordinates for a prime, b prime, c prime, and d prime. And with that, it wants us to determine a, the two-dimensional position function describing the motion. And then following that, b, the two-dimensional displacement function describing the motion. So remember before, we were always given either the position function or the displacement function. And now we're not. Instead, we're given a picture. And using the coordinates of the original position and the deformed position, we can actually create those equations, the position function and the displacement function. So that's what part A and B is like. And this is why you guys probably will hate me for it, is because this is something we haven't really done or studied before. So we can say, okay, well, I know what you're saying, but I don't know how the hell to do this. So we're going to go through it, and hopefully you guys can see, oh, that's how you do it. And oh, this question's not as bad as it looks. And finally, we wrap up the question with part C and D, which is find the displacement gradient and the deformation gradient. And we remember that if we have the position function or the displacement function, part C and D is a piece of cake. The real trick to this question is going to be, okay, how do I find the position function or the displacement function? So let's just kind of take a step back and say, okay, well, what exactly are the position functions? And I remember that for two-dimensional motion, our position functions are going to be x1 and x2. And they're going to be functions of big X1 and big X2. So what I can do is I can say that x1 is equal to some constant plus x1 with some coefficient plus x1 squared with some coefficient, and so on and so on. Now here's the real trick to remember. X1 can have big X1, but it could also have big X2 in it. And of course, I want to make another note saying that we can have higher orders. So notice how I stopped at when I got to x1 squared and x2 squared. There could be an x1 cubed or an x1 to the fourth. But of course, that's a bit too mean, so I guess this will be my first hint in saying that you should not have an x cubed or an x to the 4 or anything like that. So in its current state, we're going to assume that our position functions x1 is going to be a function of x1, x1 squared, x2, x2 squared, and then some coefficient. So I represented the coefficient as C11, C12, etc., etc. And the goal of this will be to solve what exactly are those C11, C12, blah, 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 blah. So the first hint, well, I guess the big hint that I'm going to give you guys, is when we look at this function, we're saying, okay, let's look at the relationship between A and D, as well as D and C, and so on and so forth. And what we'll see is that if I'm going from A to D, or if I'm going from D to C, or on the opposite way from A to B, these are linear lines. All four of these lines are linear. So this can be the first kind of big hint. The deformed shape, all of those lines are linear. And if they're all linear, well, how can we have a quadratic term? There must be no quadratic terms because, again, all of those lines are nice and linear. So if I come down here and I go back to my original position functions, x1 and x2, I can remove the quadratic terms from x1 as well as x2. So this leaves us with the following, where x1 is going to be some coefficient plus some coefficient x1 plus some coefficient of x2. And x2 is actually going to be the very same thing, except the coefficients can, of course, be different. So now if I look at these two equations and say, okay, well, I'm getting really close to my position function. But now I got to realize I got 6 unknowns. I got C11, C12, C14, and then C21, C22, C24. And now I'm saying, okay, well, how do I solve for these? Well, the trick is to use the coordinates that were given. Because remember, those coordinates, those are the x1 and x2. So if I come down here and say, okay, I can solve for the remaining coefficients using those coordinate points. So let's consider the very basic coordinate, which is 0, 0 to our transformed coordinate A prime. So I remember that A, for all of you guys, in the undeformed configuration will be 0, 0. And we're transforming that to A prime, and I just picked random values of A prime. You guys, of course, will have different values from everybody else of A prime. So the first step in realizing that in its original configuration, that 0, 0, what does that mean? Well, that's going to be big X1 and big X2. And after we deform it, so it goes to the point A prime, that 2 and the 4, what exactly is that? Well, that's going to be small x1 and small x2. So if I come down to my equation above and say, okay, well, I know that x1 and x2 is equal to this, so I go down c11 plus c12, and then my next term would be big X1. But I know in this case, at the point A, 0, 0, big X1 is 0. And then I go to big X2, well, that's also equal to 0. And I know that this X1 at this particular point, 0, 0, is going to be equal to 2. So from this, I can say, oh, okay, I'm starting to see a relationship here. And the same thing for X2. I got C21 plus C22. Oh, X1 is 0. So C22 times 0 plus C24 times X2. Oh, that big X2 is also 0. So I got two zeros there, and I know that this is equal to small x2, which in this case is equal to 4. Well, if I factor in the fact that a lot of those are multiplied by 0, just like this, I can quickly see that, oh wait, C12 is equal to 2, and C22 is equal to 4. And now that I know these coefficients, I can start using the other coordinate points to start to solve for the rest of the coefficients, C12, C22, stuff like that. Now, oh, I guess I have a mistake here. It says C22 is equal to 4 when it's C21 is equal to 4. So I'll correct that after. But here's kind of the key here. When we're looking at these coordinate points in the original spot and want to try and find relationships, always start with the coordinate points that have the most zeros. Because notice how since I had a 0 there, I was able to start canceling a lot of those coefficient terms. So if I were to go to my next coordinate point, we have a bunch of options. We have 0, 1, we have 1, 0, and then we have 1, 1. Now, again, we always want to go to the coordinate points that have the zeros in them, because those will cancel things. If I were to use the coordinate point 1, 1 next, well then none of my coefficients will cancel, so therefore I might not be able to solve the equation. However, if I pick the coordinate point 0, 1, well then I can see, okay, well there's a 0 in there, all my x1s are going to cancel. So that's why we use these coordinate points, and more specifically, the coordinate points that contain zeros to start solving for these coefficients. So this is how you find the position functions. And I guarantee you this will be the hardest part. After this, the rest of the assignment is actually, well, I guess the rest of the question is pretty easy. I'm not going to say assignment because question 6, the bonus question might give you a little surprise. So moving forward, if we have the position function, we can now determine the displacement functions because again, there is a relationship. So we know that x, which is the position function, is equal to big X plus u. So if I have small x, and I know that big X is just x1 and x2, I can determine my position functions u1 and u2. And how do I do that? Well, I just take x1 and x2 that I solved from before, and I just subtract big X1 as well as big X2, and that'll give me my u1 and my u2. So again, this should be easy. It looks complicated, but again, should be a piece of cake. And to wrap the question up, we want the two gradients. So we need the displacement gradient, nabla as well as the deformation gradient, f. Now here's the trick. Again, we're going to have to do partial derivatives, and we all know those suck. That's a given at this point. They definitely suck. No one wants to do them. So please don't do them from both matrices. You're going to have to do them for at least one. So you can either pick nabla or you can pick f, but please don't do them for both because remember, there's a relationship between the two. So let's say I find the deformation gradient f. Well, then I'm going to use the relationship f is equal to I nabla to solve for nabla. I'm not going to do more partial derivatives on my my displacement functions, even though I know them. I would rather use a relationship to save time. Because again, going back to midterm, you guys are third years now. You guys know the trick. The trick is finishing the midterm fast. Time is always kind of the worst part about a midterm or a final. So using these relationships will save you a lot of time rather than taking the partial derivatives twice, basically. So that concludes question number 5. I guarantee this will be the hardest question. If you guys understand this, then you guys are good to go, and I'll be very proud of you guys. So thank you guys so much for listening. I hope this helped. I will see you guys in question number 6 the bonus question.